Next we have exercise 3, where we have to prove proposition 12 to 15, which, if you remember, had many parts. Today we are going to prove the first 4 and the remaining we will do afterwards. So we start by recalling the parts. Of course, it's about a metric space, so let x comma d be a metric space, and this was part A. Let E be a subset of X, any subset, then E is open if and only if E is equal to its own interior. And which, of course, there was something else also here which I did not write, which is just an explanation of what this means. It means that every point of E is an interior point, and that involves having an open ball centered at that point which is entirely contained in E. We already know that part, so I did not write that part. So let us first prove this. We do the proof on that side and I write solution, although it's a proof, but because we are solving an exercise, that's why solution. Note that it's an if and only if statement, so we have to prove 2 implications, one of which is showing that if this condition is true, then E is open. So assume that E is equal to its interior, and now you consider the intersection of the boundary of E and E. Because E is interior of E, the intersection becomes this, which however is empty. Why? That's because no boundary point is an interior point by definition. Let us recall the definition of a boundary point. You have a subset E of X and you have some point, say alpha in X. Then alpha is called a boundary point of E if alpha is neither an interior point of E nor an exterior point of E. So by the definition of boundary point itself, no boundary point can be an interior point, and that is why we already know that this intersection is empty. But what does that mean? It means that this intersection is empty, which means that no boundary point of E, which are what we have here in this set, is inside E. E may or may not have boundary points, but even if E does have some boundary points, they are not inside E. But then by the definition of open sets, E is open. So that's how, if this is true, then E is open. And now we have to prove the converse. Firstly, we assume that E is open. Then by the definition of an open set, E does not contain any of its boundary points. That is, the intersection of E with its boundary is empty. Okay. Now let us recall some things that we already know. We know that every set is contained in its closure, and we have recently also known this fact, which we proved in the previous video. In the previous video, or I think the one before that the closure of E is actually the union of the interior of E and boundary of E, which means that E is a subset of this union, but at the same time E has nothing to do with the boundary. That means it does not intersect the boundary. So obviously E has to be a subset of the interior then, because it does not intersect boundary. But at the same time, we already know that the reverse inclusion is true. In fact, this reverse inclusion is true for any set E, not necessarily open set. So now you have this as well as this. So from these two, you have equality. So this is part B. Again, let E be a subset of X. This time the statement is this. Then E is closed if and only if it contains all of its adherent points. You recall the definition of a closed set. A set is called closed if it contains all of its boundary points. Now, however, we are claiming that a set is closed if and only if it contains all of its adherent points. And accordingly, we start the solution with the definition of a closed set. E is called closed if E contains all of its boundary points. So from that we have this equivalence. I write it like this because we are next going to consider only equivalences. So instead of the statement E is closed, you can now use this statement that E contains all of its boundary points, which is actually what it means. Now you recall this fact also. This is always with us, regardless of what set E you have, that the interior of E is always contained inside E. And now you start with this statement. The boundary of E is contained in E, which in other words is just telling you that E is closed. So this is a subset of E. Interior is also a subset of E. So their union of course could also be a subset of E. But what is that union? This union by a previous result is nothing but the closure of E. So you have proved that if E contains all of its boundary points, then E also contains all of its adherent points, because the closure by definition is the set of all adherent points. That's what you wanted to show, but that's not all. You have to prove that the converse is also true, which is actually easier to see. If you start instead here, which just means that you are assuming that E contains all of its adherent points inside of it, then this implies this. Why? Because you know that E bar is the interior of E union the boundary of E, and that automatically implies this. Why? Because del E is a subset of this union, because that's just coming from set theory, right? Del E is one of the sets in that union, so obviously it's a subset of the union, and this itself is a subset of E. So that's how this is a subset of E, and that tells you that E is closed. So E is closed if and only if E contains all of its adherent points inside of it. Just like I did not completely write the statement of part A, I also did not completely write the statement of part B. If you recall that result where we showed that E bar is this union, there was something else also. Namely, we had this fact that a point of our space will be an adherent point of E if and only if there exists a sequence of points in E which converges to that point. So what does that mean now? Now that we have this additional fact also, it just means that a set E is closed if and only if for any sequence of points in E which converges to some point in the metric space, that some point has to lie inside of E. That's what it means. Next, let us see what part C is. And next we have part C, and here we have a point x0 in X and a real number R which is positive, so that we can consider this ball centered at x0 having radius R. And the claim is that this is an open set. And then we also have this other set also, which is also like a ball, but the definition is slightly different from that one. It is the set of those points x in X whose distance from x0 is less than or equal to R. There we have those points whose distance from x0 are strictly less than R. And the claim here is that this is a closed set. In the original statement, no name was given to this set, but I have called it A. It will be convenient to write the solution. So we start the solution by taking any point y in the ball centered at x0 having radius R, dx0, R. Now we are going to consider another ball whose center is this chosen point y and whose radius is S. What is S? S is R minus the distance between x0 and y. And we are also saying that note that S is positive, and that is why we are able to consider this ball. How is S positive? S is positive because the distance between x0 and y is less than R. And why is that so? That is because y belongs to this ball. So by the definition of this ball, d of x0, y is less than R. So r minus this is a positive real number. Okay. Now what is the purpose of choosing this ball? New ball whose center is y. Our aim is to show that this ball is contained inside this ball. And what will that give us? That will tell us that y is an interior point of this set. I mean, the ball is after all a set in our metric space. And y will then be an interior point, because if you recall, the definition of an interior point says that a point in the metric space is an interior point of a subset if there is a ball centered at that point which is entirely contained in the subset. So our aim now is that y is contained inside another ball which is this, which is itself contained entirely inside this. That's what we are trying to show. And the radius of this ball that we have guessed is S. And let us now see if it works. So our aim is to show that this by comma s is a subset of this. So to show that, we take any element z in by comma s. What does that mean? It means that the distance between y and z is less than s, because that's what the ball means. But s is this r minus d of x naught comma y. Now we straight away consider the distance between x naught and that point z. That is because our aim is to show that this z is inside this ball. So to show that thing, obviously we want this distance to be strictly less than r. But using triangle inequality, this distance is less than or equal to the distance between x naught and y plus the distance between y and z, which is actually less than r, and that comes from this inequality. You just have to add d of x naught comma y to both sides. The left hand side will be this plus this, and the right hand side will be r. So that's how, yes, we have got what we wanted. The distance between x naught and z is really less than r. Thus, we have to now write the conclusion. So we write the conclusion that because of this fact, z belongs to this ball. But z was any element in b of y comma s. So that's how b of y comma s is contained in this. But y was here any chosen element in this ball itself, and you have shown that you can trap or have a ball that is trapping y inside of it as its center, which is entirely contained in this set. And that's why y is an interior point of this ball. But y was originally any point of the ball itself, so that's why every point of the ball is an interior point, or in other words, that the ball is a subset of its interior. But you have the reverse inclusion already, and that's why the ball is equal to its interior. And that is why by part A, the ball is an open set. And next we have to prove that our set A, which is that closed, we are calling it the closed ball centered at x naught having radius r, that's a closed set. And to do this, we are going to take the help of part B. This is what we are going to show that I talked about just now. To prove that our set A is closed, we will take any sequence of points in A which converges to some point in the metric space. Now all we have to show is that that some point, that limit of the sequence, is actually inside A. So that's what we did. Let xn be a sequence in A means all these xn's are points in A, such that, I mean, that converges to some point y in our metric space X. And our aim is to show that y belongs to A. Now for all positive integers n, let us consider the, if this does not have n but n will come. The distance between y and x naught by the triangle inequality is less than or equal to the distance between y and xn plus the distance between xn and x naught. Okay. Oh, this will not be strict inequality. This will be ordinary inequality. Now what do we know about these distances? D of xn comma x naught. For any positive integer n, xn is a point in A. And what does A have? A has those points whose distances from x naught are all less than or equal to r. So that's why this distance is also less than or equal to r. So you now have an inequality involving sequences of real numbers. On one side of the inequality, you have a sequence which does not change. All of its terms are equal to d of y comma x naught. This is the real number, right? On the right hand side, also you have a sequence where the terms may change. As n changes, this real number may change. But anyway, it's a sequence. And the nth term of this constant sequence is less than or equal to the nth term of this other sequence. Alright. So what do you know about the limits of these sequences? Let us first recall what we are trying to do here. We are trying to apply the comparison principle here. You remember, long ago we had the comparison principle, which tells us that when we have two sequences which are related like this by an inequality and both of them are convergent, then the limit of this sequence is less than or equal to the limit of this sequence. Are they convergent? The left hand side sequence is convergent because it is constant sequence. What about the right hand side sequence? The sequence xn, you do not confuse between this sequence and this sequence, okay? Here all the terms in this sequence are real numbers. In this sequence, however, the terms are points in the metric space, particularly in A. So we are saying that xn converges to y, but then we have already seen when we started metric space theory that in that case the sequence of distances between y and xn converges to 0. So that means this alone, this term or this type of terms give you a convergent sequence of real numbers. So if you add the constant r to the terms, then also you get a convergent sequence by one of the limit laws. So all in all, you can take limit on both sides of this inequality. So that's what we did, and we straight away wrote this. If you want, you can at least write, so by the comparison principle we have this. The left hand side limit is just that constant and the right hand side limit is this, which you know is r because the first term of this sum itself converges to 0. So that means what? You have proved that the distance between y and x naught is less than or equal to r. So by the definition of the set A, y then belongs to A, and that's what we wanted to show. So it tells us that if we take any sequence of points in A which converges to something in x, then that something has to belong to A. But these somethings are what? These somethings are precisely the adherent points of A by that theorem. That I think it was the lemma which we proved in the previous video. So that way all adherent points of A are inside A, and that is why by part B A is closed. And finally for today, let us see part D, which tells us that for any point x naught in our space X, the singleton set, the one point set consisting of x naught is a closed set. The proof of this fact is very trivial. Trivial means it's easy actually, I should not perhaps say trivial. And we are going to use part B. So what does that mean? It means that we are going to see what type of sequences we can think of which have all their terms inside this set and which are also convergent, and then we will see whether the limits of those sequences are inside the set. Then by part B, the set will be closed. Now the set has only x naught in it. So the only sequence of points in this set you can think of is the constant sequence, all of whose terms are equal to x naught, which obviously converges to x naught itself, and that's inside this set. So by part B, this is closed. That's it.